There are two types of physical quantities. Number one, we shall look at what we call fundamental stroke basic quantities, basic physical quantities. Then we shall say that these are physical quantities or these are quantities. These are what? Quantities. These are what? Quantities which cannot be expressed. Which cannot be expressed in terms of any. Which cannot be expressed in terms of any other quantities by using any mathematical equation. E.g. mass, length and time. That's number one. Number two, we have derived quantities. We said these are quantities that can be obtained, from basic quantities. Then we say e.g. density, that's one. Now area, volume, pressure, etc. Then we shall go ahead and we look at what they call dimensions of a physical quantity. Dimensions of a physical quantity. We shall say that this is the way, a derived quantity is the way derived quantities are related to basic quantities of mass, length, and time. Okay? The symbol is we shall use the curved bracket to show the dimension, the symbol of dimensions. Then we shall say dimensions of mass. We shall use the capital M. Dimension of mass, capital M. Then dimension of length. We shall use capital M. Okay? And then dimensions of time. We shall use capital T. Capital T. Then we can go ahead and look at dimensions of area. area is length times length, or side times side, okay? So we shall now say dimensions of length will be, if this is length times length, that means that dimension of length times dimension of length, which becomes L squared, okay? Then dimension of volume, volume is of a tube, length times length times length. So that's L times L times L. That's L what? L cubed. Dimension of density. Density is equal to dimension of mass divided by dimension of what? Volume. Mass is capital M. Volume is L what? Cubed. So this will be capital M, L negative what? To power negative 3. Then we can have even others, okay? Dimension of acceleration. Acceleration. This is dimension of force, okay? Times dimension of mass times what? Times acceleration. No. It is acceleration by definition is rate of change in velocity. The rate of change in what? Velocity. So it is dimension of change in velocity. Change in velocity over dimension of what? Time. But dimension of velocity is equal to dimension of distance over dimension of what? Time, which is L over t, that's L over t negative what? 1. So we substitute dimension of acceleration, therefore will become, we will now finally become L over t negative 1 divided by t, which becomes L over t negative 2. Dimension is of momentum. So sometimes you can get dimensions by using the standard units, the SI what? Units. So we shall now say dimension of momentum Of course we know that momentum by the units we have mass, it's mass times velocity, that is kilogram, okay? Velocity is meters per second squared. Per second. So we shall now say kilogram is for mass, that's capital M. Meters is for length, that's capital M. Second is for time, that's capital T. Capital T with the negative 1. Yeah. Okay? Then what about for example force? Dimension of force. Now force is MA. Force equals M what? Force equals M what? MA, which will become mass is kilogram, acceleration is meters per second squared. So we substitute. So it will be kilogram for mass, meters for length, second squared is for time, negative 2, and etc. and etc. So we can use the unit. We can use the units to get pressure. Okay, let us end with pressure. Dimensions of pressure will become pressure is force over area. So the force already is kilogram, meters, S negative 2 divided by area. Our area is meter squared. So we shall have pressure, it will be mass, meters times length, second squared is T negative 2 divided by meter squared is L negative L squared, which becomes, this is it, this will cancel with this, we shall have L negative 1, T negative 2. Then we got uses of dimensions. Uses of what? Uses of dimensions. Uses equation is. One, to check validity of equations. Of equations. Number two, to drive what? To drive equations. To drive what? Equations. Then we shall start with the first one. Check. We start with the first one, which says to check what? Validity of the equations. Of equations. Then we shall say that equations are said to be dimensionally correct. Equations are said to be dimensionally correct. Correct. If dimensions of left hand side is equal to dimensions of right hand side, e.g. V is equal to U plus LT. Show that the equation is dimensionally correct. So we shall start with dimensions of left hand side is equal to dimensions of V. But V is meters per second. Meters is length, per second is t negative 1. The dimensions of right hand side will become dimensions of U, okay? Plus dimensions of A, which will become dimensions of U is L t negative 1 plus dimensions of AT. A is M is meters per second squared, so that is L t negative 2 times T, which will become L t negative 1, okay? Then times what? L t negative 1. Let me write it up there. So it will become L t negative 1 plus L t negative 1. When you add them, these are two. L t negative 1. Then 2 is dimensionless constant. It has no dimensions. Then if that's the case, we shall say that since dimensions of left hand side is equal to, you can see this dimensions, the dimension here, dimension is here, and dimension is there, they are the same. So since dimensions of left hand side equals dimensions of right hand side, then the equation is what? The equation is dimensionally what? Consistent or correct. Consistent or correct. That's number one. Number two, we can also say, okay? Number two, we can also say the velocity V, the velocity V of the wave is given by. So we have this. They are saying that the velocity of a wave in a string is given by that. So the velocity is given by V equals square root of tension times length divided by mass. Show that the equation is dimensionally correct. So what we do? We start with the dimensions of one side. So we shall say that dimensions of left hand side is equal to dimensions of what? Of V. But dimension V is velocity, which is meters per second. Meters is for length, second is for time. So it is L t per that. Then a dimension of right hand side will be equal to dimensions of square root of TL divided by what? By mass. which will now become square root of tension. Tension is the force whose dimension is given by what? Tension is the force, but force is what is MA, isn't it? But M is kilogram, so it is MA. So that is mass is kilogram. Okay. Mass is kilogram, so it will become capital M. Acceleration is meters per second square. Meters is L. Second square is -2. Times length is L. Divided by mass. Mass is capital what? Capital M. So this will cancel, and then this and this one is to be, the answer is going to be square root of, we can take it to power half, okay? This is L squared times T -2 to power half, open brackets, this will be L T -2. Since dimensions of left hand side is equal to dimensions of right hand side, then the equation is dimensionally correct. Dimensionally correct. So we go to number what? Next question. Next question. Number what? Number 3. We go to number 3. Number 3 we shall now say. So they are saying number 2 that show that v squared equals u squared plus 2as is dimensionally correct. So what you did in this case, you will say we start with the dimensions of left hand what? Side. Okay? So that means the dimensions of v squared, okay, will become, this is meters per second squared, so that is L T meters per second -1 squared, which is L squared T -2. Then we go to dimensions of right hand side. So we shall not say which is equal to dimensions of u squared plus dimensions of as. 2 is dimensionless constant, and the dimension of the constant is 1. You understand? Dimension of the constant is what? Is 1. So 2 is a dimensionless what? Constant. So we shall now say, now this is L T -1 squared, because it is meters per second, what squared? It's for meters per second, plus, here we shall have, this is meters per second squared, that is L T -2, okay? Then times what? Times L. So this will be L squared T -2 plus, this is L squared T -2, which gives us 2 L squared T -2. So since, okay, we complete now. Since dimensions of right hand side is equal to dimensions of left hand side, the equation is correct. The equation is dimensionally what? Correct, like that. So now, in this case, when we're adding, we add quantities which have the same units. Any equation that has addition must have addition or subtraction must have the same units. Therefore, we add the quantities or subtract quantities which have the same dimensions. However, we can multiply or divide the quantities of different dimensions or of different units. Okay? You cannot add time and length and get what? You cannot add mass and what? And length. You have to get what? But you can multiply time and length so that you get centimeter second or centimeter per second, etc. Okay? So take note of that dimensions are used in equations that involve adding, which have the same physical quantities. Okay, which have the same physical quantities or which have the same units. Is that clear? Then let us go to the next one. Let us look at another use of dimensions. Next, we look at to drive number 2. To drive what? Equations. To drive what? Equations. So we shall now say here in this case, okay, we shall now say the method of dimensional analysis is used to obtain the method of dimensional analysis. Dimensional analysis is used to derive equations or to obtain equations to obtain an equation which is relating to obtain an equation relating variables. E.g., examples. We're going to look at 2 examples. Number 1, we look at 2 examples. So we have this. The period of pendulum bob depends on the mass of the bob, the length of the pendulum or the length of the string, and acceleration to gravity. Derive the relationship between T, M, L, and G. So that means that the period T depends on mass, T depends on L, T depends on what? G. Now let's combine those equations. It means that T depends on M, L, G. But then we don't know the powers. We don't know this power X, we don't know this power Y, we don't know this power Z. But those powers, we can get them by using dimensional analysis. So our T will become a constant, okay? M to power X, Y, sorry, L to power Y, G to power Z. So you said dimensions of T is equal to dimensions of M to power X times dimension of L to power Y times dimension of G to power Z. Like that, okay? Then we shall now say where K is constant, where K is constant. So we have dimensions of M to power X. So here X is out. X is not part of dimensions. Y is here. Z is here. Okay. So this is period. Period is what is time. Okay. Period is what is time. So our time, the dimensions of time, because it's seconds, so that is capital T. Capital T will become, this is capital M to power X, capital L to power Y. G is acceleration to gravity, which is meters per second squared. Meters, it will be M T negative 2 to power Z. So our T will become M to power X, L to power Y, L to power Z, T to power negative 2Z. So our T will now become M X. This you add when the multiply bases, numbers of the same bases, you add the powers. So this will be L Y plus Z. Then times what? T to power negative 2Z. It can be written as M to power 0, that is 1. Then L to power 0, that is also 1. Then T to power 1, of course, is equal to M X L to power Y plus Z. Then T to power negative 2 to Z. So let us equate the powers of dimensions on left hand side and right hand side. So mass has 0, so we shall say that X or X will become 0. Okay? This X will become 0. Then Y plus Z y plus z is equal to 0 also. Then we go to equation 1. Okay? Then we have negative 2z is equal to 1. There's 1 here. Negative 2z equals 1. So z will become negative 1 over 2. Then substitute here, y minus 1/2 is equal to 0. That means that y is equal to 1/2. Now we substitute, so our t becomes k times m to power 0 times l to power half times g to power negative half. Okay, so it means that t will become k. This is l over g to power half. So our period t will become k square root of l over t over g. That's number 1. We look at number 2. So we have number 2. Use dimensional analysis to show how the velocity of a wave depends on length, mass, and tension. So here we shall now say that the velocity v is proportional to the first one is what? Is it length to power x, mass to power y, tension to power t, to power z. So meaning that velocity v is equal to constant, okay, L to power x, m to power y, t to power t, z. So we are going to use dimensional analysis to get the values of x, y, and z. So dimensional velocity v. Now the dimension of what? Dimension of a constant, okay, is equal to 1. That clear? Will be dimension of L, dimension of length L, but then the power is what? Is it power x times dimension of mass, but the power is what? Y times dimension of tension to power t, z. So this is velocity meters per second, that is L t negative 1 is equal to this capital L x times this capital M, that's y, times tension is a force, and force is what? Is MA. Mass times acceleration, which will be mass is a capital M, acceleration is L t negative 2 squared to power 2, then this is power z. So L t negative 1 can be written as L x M y times M z L z t negative 2 what? To z. Okay? So it means that m to power 0, L to power 1, t to power negative 1 should give us this and this, that is L to power x plus z times m to power y plus z times what? Times t to power negative 2 z. So we shall now come and say, equating the dimension 0 is equal to x y plus z, y plus z. Okay? Equation what? 1. Okay? Yeah. Then equate for L. L is 1 is equal to, here is x plus what? Equation what? 2. Then for t negative 1 is equal to negative 2 what? So what z will become a half. Put z in 1. So our y will become negative what? A half. Then put z in 2. Our in 2, what is 2? 1 is equal to x plus a half. So this one comes here, so our x becomes a positive of what? A half. Then we substitute down. What will be now the final equation? The final equation is going to become here. V is equal to K L to power X. Our X is a half. Times M times M to power negative half. Okay, this is negative half. Times T to power what? Z is a half. Z is a half to power a half. So this one is the same as V is equal to K L to power half, T to power half, divided by M to power half. So we shall now find a half V. It is K square root of T L divided by plus. So then we can also look at another one. I hope this one is clear, not so? More examples. More what? Examples. More examples. We proceed. We are saying that for streamline flow of a non-viscous incompressible fluid, this equation relating pressure, density, and H is height, by the way, where H is height. This is the equation. Now, where P is pressure, density, acceleration to gravity, height, density, velocity. So let's say that A, B, and D are what? Are constants. So if the equation is dimensionally correct, meaning that it is scientifically proven that it is correct, therefore, use dimensionless analysis. Find the dimensions of constants A, B, and C. Okay? A, B, and C. So when I say that the dimensions of a constant is the constants are dimensionless correct, they are dimensionless. Okay? But these constants here, I'm referring to constants which don't have units. Which don't have what? Units. Now, since we have pressure, P minus A, obviously A must be pressure, because you cannot subtract pressure, you cannot subtract quantities of different units. Then this is H minus B, this is H is height. Obviously this one should also be distance. This one is velocity. Obviously this one should also be what? Velocity. Therefore, these ones are not dimensionless constant. Not so? They have dimensions, though they are constants in this case. So they are telling us we don't know them, but we can find their dimensions. Okay? So when we are subtracting, or adding, we add the quantities which have the same units. So in this case, it means that if I'm adding, that means that those two quantities I'm adding must have the same units and therefore must have the similar similar dimensions. Now, like for example, P, I will say take dimension of A. Dimensions of A will be same as dimension of pressure. And pressure, we say that it is force over area. Okay, that is force. That is M. L T negative 2 divided by area, which is L squared, giving us M L negative 1 T negative 2. Then dimensions of B should be equal to dimensions of what? H, which is length L. H is in centimeters, so that is length, not so. Then dimensions of D will be equal to dimension of V, then squared, which is, that is L, T negative 2, but then what? Squared, which will now become L squared, T negative what? Negative 4. So that is how we get the dimensions. So I can now put the exercise here. I can now put the exercise. I can now put the what? The exercise. So we have this as the exercise. The velocity v of sound traveling along a load of Young's modulus y. The density is this one. So show that this equation is dimensionally correct. Also, this one also saying that the centripetal force is given by this one, where m is mass, v is the velocity or speed, and this is radius of the circular path. Show that this equation is dimensionally correct. Then we are also given this one. This is a volume of liquid flowing. This is a time. This is a constant. This is the radius of the tube. This is a pressure, and this is length this is coefficient of viscosity whose dimensions have been given. So find the value of x using the method of dimensions. So in this case, they will ask you questions. For example, they can say, distinguish between derived quantities and fundamental quantities, stating 2 examples of each. Then they can say, what is meant by the dimension of a physical quantity? What is meant by dimension of a physical quantity? Then they can say, describe briefly one application. Describe briefly one application of dimensions of a physical quantity. Describe briefly one application of dimensions of. So if you have to say, for example, that you use dimensions in showing that the equations are dimensionally correct, or in checking the validity of the equation, go ahead and say that equations are said to be dimensionally correct if dimensions of left hand side is equal to dimensions of right hand side, then the equation will be scientifically correct. Yeah. Or you can also use the other one for doing what? For deriving the what? For deriving equations. Equations can be derived using the method of dimension analysis. Okay? So that the variables can be related. Is that okay? So this is brief about the dimensional analysis or about the physical quantities. Is that okay?